All right. Happy Friday afternoon, everybody. I hope you're gearing up for a good weekend. I do have a lesson for you today on volcanoes. And we're going to kind of throw in the most important information or pertinent information on ocean floors here as well. Also, sorry about my camera. It's not working. I don't know what's going on with it, but it's been having trouble all day. So please forgive me for that. Still looking at standard 2-1. I told you guys at the beginning of this unit, man, this one is heavy. It's a heavy hitter. So 2-1, how the internal processes, we'll get to external next unit, but internal processes form and modify continental and oceanic crust, okay, throughout all of Earth's history. So what we're looking at today, the first part of this lesson, um, what causes volcanoes? How do we link what we just learned with plate tectonics into this catastrophic event that we're working on now? Um, and then the second thing is about how constructive and destructive volcanic eruptions can be. So it does some good things for us, and it does some bad things for us, clearly. So the first part here is just going to be some fun facts, some things you may not have known. Volcano comes from the name Vulcan, which was the Roman god of fire. Also, I put on here one of my favorite volcanoes, the Kirchhoffel in Iceland. Beautiful. Want to go there one day, but bucket list. Side note about Dr. G. Fun facts: there are about, this is an about number, 20 active volcanoes. Um, and I will show you those in just a few minutes. I'll show you a map of that. I do need you to know this. My students, please screenshot this part and put it in your Unit 3 folder so you have this as your study guide. It's not just lava that erupts, and this is a very, very common misconception. It's not just lava. We talked in class that, we get the fact that there's gas and there's ash that comes out as well. So not just lava, but there's other stuff too. We call these pyroclasts, and these are the other objects that are ejected. Ash being the smallest, like powder, that carries great distances, goes up miles, can go up miles into the atmosphere, and then it can be carried on the weather patterns throughout and scattered throughout large distances. And we're going to talk about that more when we get to atmosphere next chapter, next unit. Cinders right here in the middle, you can see those red looking rocks. Those are called cinders. So, about the size of a quarter, maybe a little larger than that, just a normal size rock. Those can be ejected. And then we have bombs, which I think are the coolest. We call these things bombs, but these can be upwards the size of a school bus. But this one I got here for you, this picture, you can see this woman standing beside this great gigantic rock. Just think about the impact that would have being ejected out of a volcanic eruption over a large distance. So, ash, cinders, bombs, you need to know those as pyroclasts. Also, cool fact here, y'all know I love space. Space is one of my favorites, so I had to add this in here. The tallest volcano in the solar system is not found on Earth. So you can look at this down at the bottom, Mont Blanc, and then Kilimanjaro. You got Mount Everest there. And so Olympus Mons is on Mars, and it is obviously way larger. You can see the red in the background, way larger than anything that we have here on Earth. All right, this is the tough stuff. To the important things here. That should say caldera. I need to fix it. There should be an A on the end of that. The anatomy of a volcano. You guys were so surprised that I used that term when we were talking about earthquakes. Like, what are you talking about? The anatomy. It has body parts, and you need to know them. So the ash cloud is important. You can see that up top. Again, that's where those pyroclasts are going to be, ash clouds. We have the main pipe. I added that to this image, but this main pipe is its main vent. You may also see that central vent, that word too. And underneath every active volcano, this is a quiz question. Underneath every active volcano, there's a magma chamber. You're going to see in the video, like we were talking about, you saw this in your plate tectonics, your gizmo. Actually, let me share this tab instead. So I've got that pulled up already. But when we did boundary B, C, boundary C, you could see that magma chamber here, right? It's created at that convergent plate boundary at a subduction zone where it's extremely volatile. So the melting of that rock, that plate right there, energy has to be released. That has to be released somehow. And that's what volcanoes do. They release that energy, that tension that's building up down there. And that magma chamber is what sits just below. That magma gets pushed up when activity occurs. Two words that you do need to know here, and be mature about this first word. Dike is a vertical intrusion. You guys remember that word we were talking about in our interpreting geology lab, right? We had an igneous intrusion in that cross section. Let me get back over here and share. My bad. Um, there's the dike right there. We have an igneous intrusion in that cross section. It's the same thing here. This is an intrusive igneous intrusion that is vertical. And it's kind of like yin to the yang is a sill. A sill is the same thing. Again, an intrusive igneous intrusion. And it is horizontal, as you can see there. So the only difference between the two, besides the names, is that one is vertical and one is horizontal. Okay. We also have in many composite volcanoes, stratovolcanoes, which we're going to learn about in just a second. They have a lot of these side vents, so places in which magma can come out sometimes that is off of that central vent. And then, of course, you need to know the difference between magma and lava, which we've talked about a lot. Magma being interior, and then when it comes out onto the surface, we call it lava. So those are identified as well. Magma, you could use any of this, magma chamber, and then lava, of course, when it comes out onto the surface. And the last one here, and again, I misspelled that. I need to go back and fix it, and I will. Is the crater. In active volcanoes, we do call it the crater. And a lot of times when a volcano becomes dormant or inactive, then it leaves this large gaping hole. Let me see if I can get a picture of that. Crater Lake is an example of this. Beautiful. Look at that. It's absolutely gorgeous. Okay. Crater Lake National Park. But what this is you're looking at a caldera there. This is a dormant volcano, and of course, over time has filled with water in its crater and now is Crater Lake. So a beautiful feature for us to look at. So you are responsible for knowing all of those parts, okay? So this would be something I would screenshot and put in my Unit 3 folder. In class, we're going to do this in class, so I'm not going to take time to do it now because it's just notes. But when you do this on your self-paced, all you need to do here is put the number. So where you see the magma chamber, take your little crayon down there, whatever color you want, and just put the number. So 1, okay? Identify a dike and a seal. That may be difficult on there, but do your best, or you could draw it out to the side if you would like. But again, we'll do that in class. I am going to play this video because it's wonderful and it's only 3 minutes. Please give it your undivided attention.
Volcanoes are our most explosive landforms, able to eject molten rock and clouds of thick ash high into the atmosphere, with devastating consequences. Volcanoes mostly occur along destructive and constructive plate boundaries, where plates are pushed together or dragged apart. Cracks or weaknesses allow magma to rise up from below the Earth's crust. Pressure builds up, which then releases suddenly, causing the magma to explode. A volcanic eruption. Magma that reaches the Earth's surface is called lava. This molten lava eventually cools to form new rock. After more eruptions over time, a mound of rock builds up, forming a cone-shaped volcano. Volcanoes all have the same key structure. A collection of magma underneath the volcano forms a hot, bubbling furnace called the magma chamber. The main vent allows this magma to escape, and secondary vents are smaller outlets the magma can travel through. The caved-in surface is called the crater. It's created after an eruption blows the top off the volcano. Eruptions occur when pressure forces magma from the chamber up the main vent towards the crater. If the ash and mud from a volcanic eruption mix with rainwater or snow, it creates fast-moving mud flows. The hot lava and overwhelming mud flows can destroy huge areas. However, volcanoes are also essential for life on our planet. Scientists believe that volcanoes formed Earth's first atmosphere by spewing water vapor, sulfur dioxide, nitrogen and carbon dioxide into the air. And volcanic eruptions continue to contribute to the carbon cycle, crucial to life, by releasing carbon dioxide. They can go through long periods of being very active, but they may also become dormant, not erupting for hundreds or thousands of years.
All right, I'm going to stop it right there. It said some really key stuff, guys, that I hope you were paying attention to. Maybe go back and watch it again. Definitely towards the end, they're talking about how volcanic eruptions can be good and can be bad. That goes back to our our essential question or driving question for the day. Um, they can be good and they can be bad. Our early Earth's atmosphere was directly affected by these volcanic eruptions, and is part of the reason why, for a long time, scientists think that life couldn't exist because there was too much carbon dioxide because of the volatile nature, many volcanoes that existed on Earth at that time. And we'll get way more into that fun stuff, talking about the carbon cycle, carbon dioxide, and how volcanic eruptions were responsible for that early Earth's atmosphere in our next unit. Okay. This website, would rather go to the website. Let's try that. This website, play around with a little bit. It's not nearly as fun as the USGS website on that we looked at with earthquakes, but it identifies all of the world's active volcanoes. And so take a minute in your spare time to look over that and see what you see. All right, we'll do the quiz in class or in our self-paced. So I'm going to move through that. Volcanoes, what do they do? What are they for? Well, they cool off and release internal heat and pressure. Again, we're talking about most of those volcanoes, most of them are sitting on subduction zones where it's an extremely volatile place. Moving through this, we'll do that in class. Let's talk about the cons. This is what everybody knows, right? Everybody knows about the cons. Yeah, it's destructive, right? It disrupts commerce, kills people, kills animals, livestock, could generate tsunami, displaces people, populations, destroys habitats and crops and cities and towns and communities, all those things, right? Talk about Pompeii. Google that one and see how destructive that eruption was. But yeah, so like definite cons to volcanic eruptions. What about some pros though? I feel like that one's the harder one to get. Volcanoes are responsible for creating new land, like the Hawaiian island chain. The Pacific plate as it moves. There's a hot spot underneath. The Pacific plate is continuing to move at centimeters per year as it does. New island chains are forming, or new islands are forming in that chain, rather. So it does create new land. Also provides habitat to pioneer species. So some of these places like Crater Lake, also in the ocean, we are finding lots of pioneering species around mid-ocean ridges and those volcanic eruptions and volcanoes under the water. Create economic mineral deposits. This is a really good one. So fertile soil, volcanic eruptions release a lot of good minerals from interior Earth, and that is very helpful for agriculture. Does create beautiful landscapes, again, like Crater Lake there, and generate tourism, of course, to those places. So there are some pros to match the cons. All right, so the next part of this lesson, we're going to talk about the three major kinds of volcanoes. And yes, there are more than three, but these are the three that you are responsible for. Okay. First one is a shield volcano. This is a volcano that sits lower to the ground. Um, it looks like a warrior shield, which you could see is why they would call it a shield volcano. But it's lower to the ground because of its viscosity. We need to talk about that word, viscosity, right? We talked about that word with interior Earth, with the layers of the Earth, but that viscosity is so important because it has low viscosity, meaning that it's going to be moving fast. All right, low viscosity means it's going to move fast. It flows many miles, and so that it doesn't have time to harden and become extrusive igneous rock there on the surface, building that mountain higher and higher. So the viscosity matters. Opposite to that shield volcano is a stratovolcano. Also, I need to note that another name for this one, and you will see these used interchangeably, is a composite volcano. Okay, these can grow to enormous heights because of, again, that viscosity. This one has very high viscosity, meaning very, very slow moving lava, which usually doesn't have a lot of time to get far away from its source. So it cools rapidly on the surface, creating higher and higher mountains. Okay, so again, kind of the opposite here, stratovolcano, also known as composite. The last one is a cinder cone. I think this one is so interesting. It's bowl shaped. It doesn't usually get high off the ground, and they are usually very short lived. Like the eruption itself is usually very short lived. Okay, so stratovolcano, shield volcano, and cinder cone volcanoes. Three majors. All right, volcanoes can, now we're going to kind of shift gears just a smidge. Volcanoes can be found on the ocean floor. We have been talking and talking and talking about mid-ocean ridges and how those are mountain ranges and how they are active. And there's lots of active volcanoes on mid-ocean ridges. Well, now we're putting it all together here, right? So volcanoes can be found on the ocean floor. Here's some pictures, mountain ranges, and these are active. There's a great picture. Oh man, there's a video. I will get it to my students, but there's a super cool video on those pioneer species that are existing, thriving, living in these places, right near these vents, which you know are extremely hot. Still 2-1 here, but this is, now we're going to kind of shift a little bit and we're moving into the ocean floor. So that was a good segue, talking about those volcanic eruptions, into what we need to know about the ocean floor. All right. Again, we've discussed a lot of this. You know a lot of it already when we're talking about mid-ocean ridges and such, but we got to have a little bit of the vocabulary down. How do we know it's down there? Remember Harry Hess? What did Harry Hess use, if you can remember? Harry Hess was a geologist, a professor of geology, but first he was in World War II as a Navyman and discovered the mid-ocean ridge using sonar. How did he make that discovery? In the, what, 50s and 60s, I do believe? Um, Modern technology. Okay, so how do we know it's down there? The answer is modern technology, right? We have been able to map out most parts of the ocean floor using some different types of technology here. Sonar is one of them, big one here. Sound waves are used to reflect off of the seafloor, and we're next week you're going to get a lot of information on waves, so this might make a lot more sense if you do this lecture the Wednesday Thursday time frame of next week. But those waves, when they hit something that's close, they're going to return faster. When they hit something that's far away, they're going to return slower. And so the speed of those waves bouncing off of those objects, reflecting off of those objects, gives us a picture of what's down there. Seismic reflection is different from sonar. Again, high energy, but the seismic reflection can actually penetrate some of the layers, rather than sonar is just going to bounce off of solid, very solid objects. But seismic reflection can actually let us know what's down there consistency wise, like the layers, the soil, the sand. Okay. And then we have altimetry or radar altimetry. And this one's super interesting, right? Because you wouldn't think that anything from a satellite would give us any kind of indication of what might be on the seafloor. However, these satellites monitor the changes of the ocean's surface, okay? Because anything that has mass will draw the water to it. It will draw, and the changes on the ocean surface indicate what large body might lie below the surface, okay? So just a couple of those modern texts there. Now we need to switch over and look at the zones. Again, this is going to be familiar to you because you studied mid-ocean ridge, and we spent a lot of time on that. All right, because we studied boundaries, because we did the plate tectonic lab, a lot of this is going to be very familiar, just with different words. Okay, so three main zones, and I would screenshot this and put it in your Unit 3 folder as a way to go back and study because this is a good one. The ocean margins, ocean basins, and those lovely mid-ocean ridges. Okay, so let's look at the next picture. This is the vocabulary you're responsible for. If you see it across the bottom, kind of got cut off there. I need to fix that. But this is the information that you're responsible for. You need to be able to identify the coast. That's the easy one, right? But then leading out where we have this rise, and I know you guys can picture the rise of the land up to the coast from the ocean floor. That is called the continental margin. And without getting into a lot of stuff you may not need, there are two types. There are active margins, and this would be like on our West Coast, California, out there where we have that convergent plate boundary where the Pacific plate is being absolutely demolished, especially up towards, we have Washington State up there, that area where the Cascades are going into Canada. Um, that is an active continental margin. That's where we talk about those deep ocean trenches, the Mariana Trench, okay, across the Pacific Ocean. This is where that pinch is, where there are the deepest known zones of the ocean. And this is what you're looking at right here on this screen. This is a passive one. That's why I'm kind of explaining in my own way here. But the active margins are going to be where those deep ocean trenches are, at those subduction zones. Okay. So the highly volatile areas, that's the active margins. Passive margin is what you see here. A passive margin has a rise, a slope, and it gets up to the continental shelf. So there's a gentle rise of the land, a gentle slope, and then the continental shelf. Of course, it sounds passive, and that's why we call it passive, right? Gentle rise. And then we have the ocean basin, and you do need to have this word in particular. There are lots of features that if we had a little bit more time, I would talk about the atoll and the Guyot, and I would talk about um, seamounts and those other types of features that are on the ocean floor. But those are not ones that you're going to be responsible for, and we don't have a lot of time for that. So this is the one that you absolutely need to know. You will have questions on this. The abyssal plain is the ocean basin, right? It's that large expanse of land at the bottom of the ocean, and it's flat, right? And that brings us on out to the volcanic island that you see there, the ridge. That is the mid-ocean ridge. Again, all major oceans, okay? The one I would love for you to think about is the mid-Atlantic Ocean ridge because that one gives us such a good picture of all of these things. Let me see if I can pull up a picture really quickly. But the mid-ocean ridge, the mid-Atlantic Ocean ridge, Atlantic ridge, see if I can get it pulled up there. It really shows us all of these things that we're talking about right here. Let me get a map. I need a good one. Oh, perfect. And this one is sonar. So let's look at this picture. Okay. So here we have the mid-ocean ridge, right? Beyond that, we have the abyssal plain. We have the ocean basin. And again, as we get closer to our continents, you can see the color begin to change. And because this is the Atlantic Ocean, right, this is a nice passive continental margin. And you can see that with that light green color, that slope, the slow rise up to the land or the continent, and then we get to the coast. So there's a good visual of what we're talking about in a real life scenario. Good. All right, so those you need to know. Coast continental margin, ocean basin, mid-ocean ridge, and abyssal plain. But want to impress your parents? Talk about passive and active margins as well. We'll do that in class, and we'll do that in class. All right. That's the last thing I have for you today. Please make sure that you have those screenshots and you put them in your Unit 3 folder. And I'll see you in class next week. Bye, guys.